estimation. And then, like I said, it's a way of using some form of statistics and probability to find the parameters of a given distribution. So distribution, of course, we have been dealing with data sets. So probably you are given the distribution of a data set and its labels. So how do you find the parameters that correctly describe that distribution, right? I won't lie, there's a lot of mathematics here, but just open your mind and try and grab something. Immediately after this, I would show us an example of where maximum likelihood estimation is being applied in the won't be too relevant, but not like it's not relevant, but based on complexity and the need as of now, we decided to skip the probability aspect of the course and move straight to maximum likelihood estimation, right? But he's saying now they're moving from probability because he did probability in the last two statistics here. And usually the question everyone asks is, if you have a data x to xm, of course we all know what m is. So it's x to xm means all the data points of the data set here. How do you find the distribution that captures this data well? So when you say how do you find the distribution that captures this data well, it's more or less like saying how do you find a way of understanding the data well, right? That's like the simplest high-level way of explaining it, right? So if you're able to understand the distribution well, it invariably means you're able to make predictions on what the outcome of an unknown of a particular let me use features would be, right? So it's usually very hard to just understand this distribution on the go, but that's why you find out that we understand this distribution based on parameters that we have set for that particular distribution, right? So it's saying that if we pick a particular parameterized family of distributions, p x of theta, right? The question will be the question is easier, right? So it's similar to what we've been doing where we have parameters theta, right? Oh, I'm not putting on this stuff. Sorry. Okay. Okay. So it's similar to when we have theta. Why is this thing? Sorry, please. Okay, so it's similar when we have theta. So it's similar to when we always had this theta parameter. What this theta is basically doing is that it's trying to understand. I think my system is hanging. I don't know. Just give me just a second. Let me share what's going on. Oh. I'm coming. Just give me 1 second. I think something is wrong somewhere. Sorry, please. Okay, I think it's fine. Okay. So it's similar to when we have, remember when we usually have something like this? Yeah. So this theta, So it's not explicitly saying this particular theta though, but if it's trying to say that if you kind of parameterize your distribution, right, this parameter theta, yeah, kind of finds or understands the distribution of your data set, yeah. So that's what it's trying to say here, and you'll find out that this is kind of applicable in your maximum likelihood estimation, as we would see in the as we move on.
Hi, Kenichi.
Yeah.
It seems there is some background noise from your
Like, seriously, it's really, it's all over my house. It's all over my house. I actually don't know where to go to now. Well, let's just see. Hopefully it will end soon. Hopefully it will end soon. Thinking of where I can go to now. Let's just move on. Yeah. Okay, so this is how maximum likelihood estimation is actually defined. So if you have a distribution P, if you have a distribution P of X given theta, yeah, that is being parameterized by theta, and a collection of observed data points. So now you have data points X to Xm, right, which we all understand. The probability of observing this data is just this. So it's trying to say that the probability that you're observing this data is the product. Okay, sorry. Is the product. So when you see this, this actually means product. Yeah. So it's the product from the first data point. That's the first data point here to M for all the data points, or the product of each of the data points. Yeah. The product of the probability of each of the data points given that parameter theta, right? So what it's trying to say is that the basic idea of the maximum likelihood is that if find, sorry please. So exactly, sorry. So what we are saying basically is that we want to kind of maximize the probability of this observed data here, right? I don't know if we get what I'm trying to say. Now you have data from xi, sorry, from xi, yeah, to xm, yeah, and then you have you want to find parameters. You're trying to find parameters that will maximize the probability of picking or giving a right prediction, basically. So you know, from the beginning, what we've been trying to do is that we are trying to find parameters that whenever you have that parameters in your model, yeah, whenever you have that parameters in whatever you call your model, yeah, no, theta x plus theta, whenever you have these parameters in your model, it maximizes the probability of giving you the correct answer. Yeah. So it's a similar thing in maximum likelihood. So in maximum likelihood estimation, you're trying to find the parameters over the distribution. Yeah. That gives that such that whenever you it maximizes the probability of you getting a correct prediction. So, but in maximum likelihood, more or less, if you know, if when we were doing gradient descent, we kind of minimize the loss. But in maximum likelihood estimation, we are more or less like maximizing the log likelihood of getting that data. So that's why you find out that we are using the log. We are using logs here, right? So it's more or less like saying, even after you have gotten this, yeah, you still need to maximize it. So that maximizing action is taking the log of this. It's taking the log of your P of xi, yeah, parameterized by theta. I don't know if you understand what I'm trying to say. I know it's quite confusing. Or Teju, do you have anything? Do you know how to explain it better? Okay, let's just move on. It should get better. I'll make it get better. Okay, so now everyone would agree with me that there are different types of distribution. Yeah. So there's something called the Bernoulli distribution. You also have something called the Gaussian distribution. You could also have a categorical kind of distribution of your data. So Bernoulli distribution is basically a binary distribution where you're having either 1 or 0, right? And what the professor was trying to do here is that he was trying to show us or he was trying to prove that maximum likelihood estimation of a particular distribution of a data here is actually correct. So, but take for example he used the example of a coin, right? So we know a coin has heads and tails, and if you are going to find the probability of having a head, it will be maybe if you toss the coin once, it's going to be something maybe 1/2, right? Or the probability of having tails. And then we also know that if the probability of having heads is 1, it invariably, if the probability of having heads is say 70%, yeah, it invariably means that the probability of having tails will be, let's assume tail is 0, yeah, it will be 1 minus 70%, right? That's 1 minus 0.7. Oh, sorry, I think I moved out of the notebook. Okay, so the probability of having tails will be 1 minus 70%. That's why we have this here. So we are saying that if the probability of the Bernoulli distribution, if we are saying the probability of a Bernoulli distribution of x, where x is equal to 1, parameterized by phi, yeah, is going to be equal to phi. And the probability of x is equal to 0, that's the probability of, let's say 0 is having tails here, it's going to be equal to 1 minus phi. So this is more or less like what the Bernoulli distribution is like. And if we are saying, let's say we have, we observe the data here, and then we want to find the probability of having a particular, let's say head, yeah, it's invariably going to be that, let's say this is head here, is invariably going to be the number of ones that we have over the total. Is invariably the number of observed actions over the total, right? This is something that everybody would probably have done in probability. So if you're saying you have, say you have 80 balls, yeah, and in these 80 balls you have, and they say okay, and then so how do I put it? You have 80 balls in a bag. What is the probability of picking 80 red balls and, let's use 50 red balls, 50, no, let me use 80 red balls. Yeah. What's the probability of picking, and you are picking balls around, what's the probability of picking, say, 20 balls? Yeah, it's probably going to be, say something, it's probably going to be, say, 50 all over 80, yeah? That's more or less like the probability of that observed, of probably taking that action is going to be, say, 50 over 80. So it's the same thing we are trying to have here. We are saying that the probability of having, say, ones, yeah, is going to be the sum of all the ones that we have all over the total number of data points that we have, which is m. This is how you solve this problem normally, right? But he now, okay, so here is saying in some other estimates, you would have something like x plus 1, m plus 2. I won't put our minds to this, but some other people will go ahead and give their estimates in this manner. But he went ahead in the later notes to use maximum likelihood estimation to show that maximum likelihood estimation will actually give this same, it is actually tending to this same answer, which everyone, which is actually the generally accepted estimate for the probability, right? So for maximum likelihood estimation, like we have said earlier, remember we said it's that we are trying to maximize the log likelihood of this, yeah? You are trying to maximize this particular thing here, right? So you would see down here that already we have defined the distribution as this. So you'll see down here that it's still the same thing. We are trying to maximize the probability, maximize the product of the probability of X given file, which is the parameter, yeah, the parameterized, or the parameter, let me use the word parameter, yeah. And X is, of course, we know it's the distribution of our data, right? So this is what we are trying to maximize, right? And because we know that the Bernoulli distribution is described this way, we have to find a way of describing this, simplifying this particular function we have written here, such that it takes account of these two different scenarios where X is equal to 1 and X is equal to 0. So that is why the formula is reduced to this. So what you will find out here is that when you say file is whenever X is 1, right, it invariably means that here will tend to 1, right, and you'll be left with file, right? So of course we know that when X is equal to 1 here, it invariably means that we're having 1 here, and this will be 0. And we know that when you have anything raised to the power 0, it's 1, right? So that means we'll be having is equal to file, which we have already defined here, right? And then when we have it as 0, it invariably means that this would be 0, and what we'd have here is 1 minus file, right? So this is more or less like the reduced distribution. This is more or less like the simplified form or the compact form of what we have here, right? Now, remember we said that we want to maximize this. What we want to do is we want to maximize the log likelihood of the data, right? And maximizing the log likelihood of the data. And we're actually taking the log likelihood of the data for some specific reasons, which we are going to look at later down the course, right? So when we take the log likelihood of the of what we have estimated here, what we'll have is this, right? What we'll have is this. So when taking the logs, this is actually reduced to this, right? Where you're having sums instead of products. Okay, so let me just say here. So now if you're having products, it has limitations here. If these values get very small, it means that this is most likely going to tend to 0 because you're having products here. But when you take the log likelihood, you're having sums, right? Which is more efficient than having this here, but we'll still see that later in the course too. So, but the results, whatever we are doing here results to this, the sum of the product of X and the log of file plus the product of 1 minus X times the log of 1 minus file. So just like we have here, if X is equal to 1 here, it means that this is going to be, it means that this is going to tend to 0, right? And if X is equal to 0, it means that this is going to tend to 0, and we'll be left with this. We will be left with the log of this and the log of this. Yeah, in each case, just like we have here, right? So the log of the sum over the sum, right? Okay, so what you would now want to do, okay, so now to bring it down for us to see how this particular expression tries to perform the same thing that you would have in the normal way of calculating your probabilities. He went ahead to find the derivative of this log loss, right? And finding the derivative, you're going to be having this, right? And this sum is for the numerators. So you don't need to bother yourself about the derivation too, but I'll go through it. So this sum, if you have it, it's going to be when you kind of multiply. This sum is actually for the numerators, not for the denominators yet. So that's why you have this here. And then if you take this as A, and you take this as B, right? Just like you have here, here, right? When you take it as A and you take it as B, of course, you know, finding the derivative means you're tending towards 0. So, and then you equate it to 0, right? you'd have the equation simplified to this, yeah? So you're having A plus B is equal to A plus B, yeah? And we know our A is what? This is our A, right? And we know our A plus B is invariably this plus this. So you might ask, how did A plus B become M? Yeah, it's M because you know that in your data sets, you're having either ones or zeros, right? So if you say X is all your ones, right? It invariably means, if this is for all your ones, it invariably means that this is for all your 1 minus X, yeah, which is 0. So it's more or less like having the sum of all the data sets, or the count of all the data sets in your all the data points rather in your data set. So you're having sum of all the ones and all the zeros, right? Is there any question? Okay. Can you guys hear me? Is there any question? Man, I think I need to leave this place. Sorry, let me look for somewhere a bit more quiet. Yeah. Well, is there any question, or do I move on? Is there any questions? I think it's quieter. It's more quiet. Okay. Can I move on? Okay. I think it's quiet now. Someone has something. Okay. So I understand if you don't understand, but I think it will get clearer when we get to the practical aspect of it too. So I'll leave out this pool. Don't think it's necessary. It's necessary to go through it. Okay, so now here, this was actually brief, but it's also trying to show you how what we did for this Bernoulli kind of distribution is applied to a Gaussian distribution. So you know, for everyone who has some math background, you know a standard deviation, right? So it's trying to say that what you would have as for the Gaussian distribution will be something like this, right? Will be something like this, as opposed to what we have for the Bernoulli distribution, which is this, yeah, this whole equation we have here, right? And okay, sorry, this ball in its simpler form, the Gaussian distribution, if you take the log likelihood, this is what you would have. And then if you find the derivatives, you'll be having something like this. So what he's also trying to do here is finding the derivative invariably means he's trying to prove the normal. So now remember, it is parameterized by two things: the mean and the mean and the standard deviation. And we all know that mean is what all the things, right? And then you find out that when you find the differential of your log likelihood, you find out it gives you the exact same thing. You're having the sum of over your data points here divided by the mean, right? And then for your standard deviation, it gives us also the normal formula for the standard deviation, which is the sum over your x minus the mean squared all over m. So it's invariably what we're trying to do here is to show that the log likely the mean the maximum log the maximum likelihood estimation it is a good way of finding the parameters of for a particular distribution, right? Okay, so to explain this log likelihood estimation, he decided to use the naive Bayes algorithm. So naive Bayes algorithm is just another machine learning algorithm that can be used to make predictions on a data set. Yeah, and the naive Bayes algorithm depends heavily on probabilistic modeling, right? So when I mean probabilistic modeling, what I mean is it has a lot of probability in it, right? And just like every other machine learning algorithm, it also uses the idea of a hypothesis function, a loss function, and then the optimization, where the loss is your maximum likelihood estimation, right? And the basic idea, right, is that you want to model X, yeah? So X is just the same thing as all the different features that we have always been talking about in your data set. And you want to know what the values of Y, which is your prediction, would be, yeah? Right. And then this distribution can also be Bernoulli, can be categorical, it can be Gaussian. Right? So what you want to find using the Bayes modeling is that you want to find the probability of getting Y given a set of features called X, right? Okay. And this is what the naive Bayes, the Bayes rule. You see, it uses the naive Bayes algorithm is based on the Bayes rule, and Bayes rule is basically this. So it says that if you have a set, if you want to find the probability of getting Y, given some values of X here, it's basically the probability of X giving Y times the probability of Y all over the probabilities of X. Yeah. And the intuition to finding this particular expression is the fact that estimating this normally is going to be a very hard task. So, but if you're going to be estimating this, like we'll see in an example below, this is going to be easier, right? You can actually find the probability of getting a value X given Y, then the probability of Y, which is just the probability of Y over the whole data, and the probability of X, which we also know. So this can be further simplified as this, yeah? But I think I'll just stick to this, right? So I think I forgot my, give me 2 seconds. Sorry, forgot my pen. Okay. So so the idea is this. So the idea is this basically. What we want to do, right, is that we want to kind of using the normal sorry, I have to move up, where you have probably, where is it? Where do we have it? Where do we have it? I'll go back to this. So where you have probably something defined by this distribution, yeah, and then you simplify it to have something around this, yeah. So this is the same exact thing we want to do in the Bayes algorithm. So now what we're trying to say represents this using a naive Bayes using with the maximum likelihood estimation that we have discussed about earlier, right? So what you would therefore find out is that for us to represent this, we can actually represent this way here. And if we are going to be representing that of y, it will be something similar, right? And for naive Bayes, if you're going to be using the naive Bayes algorithm, right? Normally what happens is that you kind of remove this denominator. Okay, let me use this denominator here for a particular reason. The reason is that what you're having here, which is the probability over x, is basically same thing as having same thing as having, say, p of x given y, right? The p of y all over p of, so now it's more or less like p of x1, x2, x3. So what you find out is that even if it is going to be a sum, you're going to find out that your denominator will remain constant over all the combinations of this numerator that you're going to be having, which invariably means that it actually has no effect on the outcome. It's more or less like a scaling factor. This denominator here is more or less like a scaling factor and actually contributes nothing to the result. So that's why you find out, if you read further, that it actually has no effect on the outcome. So having that in mind, it's what this equation will reduce to is, what it will reduce to is this, right? What it will reduce to is this, right? So where we are having, what we are having here is basically we are basically trying to describe what we have here, right? And here we are saying we want to, representing this as the normal maximum likelihood estimation. In the normal maximum likelihood estimation way, is like saying we want to parameterize this y by theta 0. So theta 0 is basically wherever we have y equals 1. Oh, sorry. Where did I keep this? So to move this into something. Okay. So theta 0 is basically same thing as saying wherever we have y equals 1. We have y. So trying to select. Okay, just work without it. Okay. So it's basically saying, you are basically saying wherever y is equal to 1, right? And if you are going to find the opposite of that, is basically 1 minus whatever we have for this particular probability, right? And we also know that y can be equal. We can also find the we have this particular expression here. Is also for, we can't. It's not more. It's not. You can't just find this as it is. Yeah, there's a case where y is equal to 1. There's a case where y is equal to 0. Right. That's where our prediction is equal to 1. Our prediction is equal to 0. And this is a Bernoulli distribution to start with here. So we are saying that where y is equal to 1, we want to have the parameter 0 of I, yeah, and then when y is equal to, sorry, this is where y is equal to 1, where y is equal to, this is y is equal to 0 rather. So where y is equal to 1, we want to have this. So we are invariably describing this particular expression we have here, this naive Bayes expression we have here, by this, right? And then we can therefore solve the parameters and have this here. So remember, we had already said earlier that for a Bernoulli distribution, the parameter would be given by this. Yeah. To find the parameters, you can find the parameters this by this. Yeah. Sorry. So for y, we can find the parameters by this. And for x, yeah, we can find x by this. So we are saying x where y is equal to 1, and all over the number of ones that we have. So it's more or less like saying if you want to predict the values of x probably being 1, is going to be the sum over all x, that is 1, over the total number of ones that we have, right? And if it is 0, you're going to say that you want to find the values of x being 0 all over all the number of points that are zeros, yeah? So that's what we mean by this expression we have here. Right? And if we are going to make predictions, right? For us to make predictions, what we basically want to do is that we want to find the values of y given x, and the values of y given x can also be, is proportional to what we have here, right? Okay. So it's proportional. Hello? Yeah?
We can't see the screen fully.
Okay. Sorry, let me try and see if is it better now?
Yes, please.
Okay. Okay, so I need to move fast so that I can go to the application. So if we want to mean is that we want to find this particular probability that we have defined here, which is similar to what we have here for using the maximum likelihood estimation, right? So it's basically the same thing as what we have here, right? So we are saying that it is the probability of y, which is this, we have calculated here, times the probability of this multiplied by this. So why I'm saying this multiplied by this is that, remember I have told you guys earlier that why we have this is more or less like a simplified expression for this, yeah? It's a simplified expression for this. So where if your x is equal to 1, you would have this, and if it is equal to 0, you would have this, yeah. Okay. So there's an example here which I would want every one of us to look at together. So just take your mind back to the normal probability that everyone would have at least encountered in school. And let's try to see if we can find the probabilities in this expression. So it gives us more intuition to everything I have been saying. Yeah. So what's the probability of the first, this first item here? Probability of y is equal to 1. You can just use the chart. Or do I need to go back? Wow, like everyone has been complaining. Do I need to go back to where I was before the screen became tiny? Okay, there's no. Okay, yes, please. Okay, so which part exactly? Where? Here? Of course, it can be here. Maybe somewhere here.
Yeah, I think it's here.
Okay. Okay, so how do I start now? Okay, so but we understand that this is how we'll define, this here is how we'll define the problem using Bayes' rule. We understand this, yeah? And we understand that because, let me put my pen. Okay. We understand that because you are going to be having something like, say, for the denominator, the denominator is going to be something like sum over x1, x2, x3, which is going to be constant for all combinations of this. We understand that this doesn't kind of have any effect in our calculations. It's, like I said, it's more or less like a scaling factor, so it's okay to ignore it, right? Okay, so that brings us, and then we also said that we can define this here based on this as using the maximum likelihood estimation that we have been talking about. You can define this by this here. So no, sorry, not we can define this by this. This is over the n. So this is more or less like for all the different features that you're having, right? So this is not just on its own, right? This particular numerator, which you're having probability of x giving y, is not on it. It's not just a single feature. It can be for more than one features, x1, x2, x3. So you can have more than one features, right? So if you're having it for more than one features, this denominator here is going to be constant, right? And then we can remove it out of the calculation. Then I went further to say that knowing that this is what we are dealing with, right? We can therefore describe this using the multi-layer perceptron, maximum likelihood estimation. Yeah, we can define it using the maximum likelihood estimation that we've been talking about. And what we'll have is this here. So we are saying that if you take the first, let's say we take this first, right? We are saying that the probability of having y is going to, if you parameterize it here, you're going to be having the probability of y parameterized by 5 of 0. And then for x, you know x, you can have x where y, for y is equal to 1 and y is equal to 0, right? Meaning we have to also take that into account. This is more or less like a Bernoulli kind of distribution, right? So what you will have is the probability of x, all the elements of x, that's all the data points, x, that's why we have xi, giving y. For y is equal to 0, so you can parameterize it. So if we say we want to denote it, we can denote it by this. And then we can have the probability of y, the probability of x giving y equal to 1. We can parameterize it by this. So that's why we're having 0 where y is equal to 0 and 1 where y is equal to 1. And then if we solve it like we did in this above, somewhere here, right? So we solve it like what we did somewhere, was it here? Yeah, somewhere here, right? What you would find out is that your file of 0 here would be this. So it's more or less like the probability all over m of all the y's over m. And so we are not using log likelihood here. We are more or less using like the straight up solution, right? We are not using the log we are not using the log likelihood, right? We're just using the straight up solution. And for y, it will be the sum over all the x where x is equal to 1 over the total number of ones that we have, right? And same thing for y, where x is equal to 0 over the total number of such y's that we have in the data set, right? And then if we want to make predictions, yeah? So we are saying that if you want to find the probability of y given x, right? It is proportional to this particular expression, which we had already defined above, which is actually equal to this. So remember we had simplified the Bernoulli distribution earlier. So this is that Bernoulli distribution that we simplified earlier and multiplied by the probability of y multiplied by the product over all the files of x, file of xi and 1 minus file of 1 minus x. So anywhere we have 1, right? This is going to tend to 0 because 1 minus, it's going to tend to 1, yeah? Because 1 minus 1 is 0 and the power of 0 is 1. And if it is 0, this will be 1. And what would have is what is left here, right? Okay, so is there a question? And can we move to the example now? Okay, so I don't know. There's no question. So let's look at this carefully. See, even if you don't understand everything I've said, right? Let's use this example to kind of understand everything I've been saying. I know it's not easy. Yeah, I understand. So, but let's look at this one carefully and see how we solve it. So, what is the probability of having y equal to 1 from this data sets that we have here? Let's do this quick so I will go to the interesting part, guys. I need to use enough time. The probability is not 0. The probability is not 0. Look carefully. The probability of having 1 in this data So what's the probability of having 1, guys? No? 4/7, that's correct. So now if you check, let me use my pen. Okay. So if you check, we have how many data sets here? We have 7, right? 1, 2, 3, 4, 5, 6, 7. So the probability of having 1 is basically the number of ones that we have here. Where is it? We have 1, 2, 3, 4. That's the number of ones we have here, all over the total number of data we have here, which is 4/7, right? Is it clear, guys? So we have, for this particular one, we have 4/7, right? What's the probability of having, probability of x is equal to 1, given y is equal to 0? So now note it is x1. 2 over what? 2/3. Okay, so let's check it because me, I don't actually know. Maybe so. Let me not can. So let's check it. So we are saying probability of x is equal to 1, given y is equal to 0. So first things first, let's even identify all the zeros. We have 0, 1, 2, 3. So meaning that our denominator is 3, yeah? And then the probability of x is equal to 1 given y is equal to 0. So we have to check for where x1 is equal to 1 and y was equal to 0. So at this point here, x is equal to 1 when y is equal to 0. X is not equal to 1 where y is equal to, when y is equal to 0. X is not equal to 1 where y is equal to 0. So our answer is actually 1/3. Is it clear? Is it clear? Okay. So since we know that one, I guess everybody should be able to do the remaining. So it doesn't mean that I'm going to go continue. No, we must do it together. Okay, so now the next one, what is the probability of x is equal to 1 when y is equal to 1? Three over 4. Okay. Let me wait for one more person to give an answer. 3/3, 1. Okay. Another answer. 3/4. Okay. Okay, let me move on. Okay, so let's check it, look at it together. So we're saying x1 is equal to 1 when y is equal to 1, yeah? So, okay, so here we have y is equal to 1. 1, 2, 3, 4. So we know our denominator is what? 4, right? So where do we have x is equal to 1, where y is equal to 1? So we have it here, 1, 2, not here. Okay, 3 here. Of course, this it is equal to 0, right? So we have it as it's actually 3 over 4, right? So it's 3 over 4. So look at it, guys. 1, 2, 3. For this particular one, y is equal to 0, right? So you can't say this is, you can't use this. I don't know if you get what I'm trying to say. It's where y is equal to 1. So you're having 1, 2, 3 over the total number of ones we have 1, 2, 3, 4. So this is what? 3 over 4. Okay, let me clean. So what's the next one? Okay, how I got the denominator. Okay, so I'm saying for the denominator, we said find what is the probability of x1 equals to 1, given that y is equal to 0. So given that y is equal to 0, it means that we are saying for all values of y is equal. So given that y is equal to 1, rather. So we are saying for all occurrence where y is equal to 1. So we are having y is equal to 1 here, which is 1. Y is equal to 1 here, which is 2. Y is equal to 1 here, 3. Y is equal to 1 here, 4. So we already know that the total number of y's that are equal to 1 is 4. You get, okay, you get it now. Okay. Does anybody still have any question? Okay, I guess we are cool. So let's solve the next one. So what's the probability of x2 is equal to 1 given y is equal to 0? So now look at this as your normal prediction thing, your data set that you want to make prediction on y. It's just the same exact thing. So now let's say we have, for the next question, we're not saying if the feature is of, if our feature x2 is equal to 1, and give what is the probability, what is our file, given that our feature x2 is equal to 1. For our x2 is equal to 1, given y is equal to 0, right? So what's that probability? 1 over 3, okay. I need another answer. Maybe one more answer before we continue. Okay, let's see small time. 1 over 3, okay. If I get one more 1 over 3, then I'll just assume it's correct. (11 over 3). I guess Obiora made a mistake, of course. I'm sure he made a mistake. It's actually, so we have 1 over 3. And that does not mean I will not check it. I don't trust you people. I don't trust anybody. Okay. Okay, so let's see. So we are saying that, so what is the total number of x or y equals 0? What we'll have here is 3, yeah? 1, 2, 3. And then we want to find all the x1s where y is equal to 0. So this is 0, this 1, this 0, so it's 1 over 3. You guys are right. 1 over 3. Okay, so what's the last one? Mind you, this is x equals 1. This is 1 here. Yeah? So what do we have here? Two over 4. Okay. 2 over 4. 1 over 2. Okay. That's correct, actually. Yeah, so that's 1/2. 1/2. Okay, so now the big question. So now, if you guys noticed, yeah, if you noticed, there was this one here. This is the unknown. Let's say this is look at this as your new data that you don't know what the value is. And then it's telling you that the X feature, X1 feature is 1, the X2 feature is 0. But what is the prediction Y? You get? So now, for this kind, how do we now solve this? So this takes us back to what we did in my base, yeah? So sorry, if I move this, whatever I've written is going to move also, so I'll just find a way to. So remember that we had stated that the solution to whatever we did is this, what we have here, right? Is what we have in this particular end here. Sorry, from here down here, right? So we already stated that, let me write it down here. So it's, we're saying our prediction of Y is equal to Y given X, whatever. Let's say our prediction Y. Yeah. Okay, I'm not writing. I thought I'm writing. So we know that it is equal to θ0, right? 5. Okay, not θ rather. This file. Sorry for the mistake. Of I raised to power Y, right? And 1 minus 5 of Y I, right? Wow, what happened? Sorry. Can you imagine? Oh boy, everything we wrote has cleared. So, but don't worry, so we know that this is what it is, yeah? Let me write it again somewhere here. I don't know, I'm not so used to this pen, and it can be frustrating. Okay, so we're saying it is θ0, file 0 rather, of this M, I is equal to 1, and file I, Y, yeah? And 1 minus file Y, yeah? So this is what it is. So we can actually use this. Remember that this is for the prediction, like we have said. We can actually use this to calculate the values to calculate the prediction here. So what you would invariably have is this. Already we all know that this is, please remind me, I've forgotten all the values. Maybe I should be looking at the chart to remember. Sorry.
4/7. First
4/7. Okay. Thanks. So trying to set up this pen. Okay. 4/7. I know this was 1/3. Am I right?
So what? Wait, I think it's 2.
I think it's 1/3. I think this was, I can't remember. I know this one was 2/4. I know this was also 1/3. I don't know what this is. Can someone remind me?
The second one is 1/3. Yeah. Okay. Then third one is 2/4.
3/4.
3/4.
Okay. 3/4. Okay. Okay. So now we want to find this here. So for us to find this, we have to find the probability. So now for us to find this, we have to find P of Y equals 1, given X 1. Equals 1. I'm too quick to put, so x1 is equal to 1 and x2 is equal to 0, right? And we also want to find the probability again of y equals 0 and x2 equals to 0, right? So now if we are going to find this, remember we had written the formula here, here, here. So what we are trying to say now is that we want to say, already we know what our x0 is. So if for this particular one here, yeah, what we'll have is this. What we'll have is our x0 is what? 4/7, right? The probability of y, the probability of x equals 1 given y is equal to 1 is what? Probability of x equals 1 given y is equal to 1 is what? 3/4. Yeah. Times what? The probability of what? X equals 0, giving y is equal. The probability of y equals 1, giving x2 is equal to 0. That's what? Okay, there's something wrong here. Okay, so that's actually going to be 1 minus. So now, if we know that this is probability of y is equal to 1, giving x1 is equal to 1. So it invariably means that the probability of y1 is equal to 0, giving x1 is equal to 1 is basically going to be 1 minus this, right? So remember we had said it here now. So now we are saying where x, remember, sorry, I didn't put it here. So you know this is x. And this is x, yeah? If x is equating is this particular term here. This particular term here, where is it? Okay. You want to ask a question?
No, I couldn't see anything you wrote above.
Here. Okay, you can see this. Let me move it a bit down. Let me see. Can you see it now?
Yeah.
Okay, so I'm saying there's x here. Sorry, I was writing on the wrong thing. Here. Sorry. And this thing is... Okay, so I'm saying here. What? Zoom is not easy, honestly. So there's x here, right? And then there's x here. I think it's I here, I'm not sure. So there's another x here, minus 1. Or rather, 1 minus x, rather. Right? So remember I told you guys that if your x is equal to 1, it invariably means this will be tending to 0. And if your x is equal to 0, this will tend to 1, right? So now I'm saying that what is the, we're not asking, we asked the question that from what we have here, right? We've computed this, right? So what about this? What is the probability of y equals 1 given x2 is equal to 0? And I'm saying that the probability of y1 is the same thing as the probability of, is the same thing as computing your 1 minus 5. So where your x is equal to 2, where your x2 is equal to 1. So here we have calculated x2 equal to, here, rather. Yeah, that was here. Yeah. So we have calculated x2 is equal to 1, given y is equal to 1 here. And what I'm saying now is that for you to find where x2 is equal to 0, yeah, so what we would have computed normally is this. But now, since we are saying x2 is equal to 0, x will be 0 here, meaning that this will be 1. What we'll be computing is this here. So we are going to be having 1 minus what we had there, which is 2/4. Do you understand? Is it clear? Is it clear?
Yes.
Okay. Okay. So similarly, right? Similarly, we'll compute the same thing for this guy here. We have to compute. So this is more or less an indication of the probability of having y equals 1 for these features that we are giving here. And the probability of having y is equal to 0 for these features we are giving here is basically going to be the same thing, something similar to what we've done above. And you all know that the probability of having y is equal to 0 is basically 1 minus what we have here, right? So we are going to be having 1 minus 4 over 7, right? Times what? I don't want to say times what? 0 giving x is equal to 1. So what's the probability of y equals 0 giving x is equal to 1? Okay, so that you don't get confused, maybe I didn't explain this. You know, sorry, you all know that this is equal to, you all will agree with me that this is equal to, like we have described, using Bayes' rule. You know that this is equal to your P of y, right? X of x giving y here, right? Don't get confused and say, well, we have x giving y here. This is what we are solving, but this is the problem that we are giving. So this problem that we are giving is equal to this, according to Bayes' rule. And now we are solving for this because it is equal to this. Do you get? Okay. So this is what? 1 over 3. Okay, no. Okay. How? But does anybody get what I said? Okay, now let me say it again. You know, okay, let me come again. You know, these problems we solved. Remember I told you it's when we had, I can't actually clean what I have on the screen now. Pardon me to just leave it there, but I'll be speaking to the slides that we have already. We have to finish soon. So remember I told you guys that this is what we want to solve, this here, right? And if you're going to, it is not easy to solve this. It is actually not easy to solve this. So you have to reduce it to what we have, what we call the Bayes rule. So with Bayes rule, this is what we have. Yeah? This is what we have with Bayes rule, this over this. And we can actually find the values of this x of y and y, and the probability of x giving y, the probability of y, and the probability of x. These are easy to solve. But to solve y giving x, it's a hard problem, right? And then we are now saying that for us to solve this whole issue this thing we are having, we want to use maximum likelihood. And we are actually applying maximum likelihood to the numerators. We ignored the denominators, right? We apply maximum likelihood to these numerators, probability of x giving y, probability of y, right? And then we have some formulas that we are already applying here. So now I'm saying that now we are calculating probability of y, probability of x, because we are using this to find parameters, because we know these parameters are going to lead us to finding a problem where we are having y given x, where we are trying to find the prediction y. Now, already I told you guys, already we are doing some calculations here. We are saying what is the probability of y equals to 1, given x is equal to 1 and x2 is equal to 0. To solve this particular thing I just said, which I wrote here, right, is not an easy task. So what we are doing subconsciously, which everybody is following and everybody gets to understand, yeah, is that we are actually solving the probability of y. We are solving this formula here. This is what we are solving. We are solving this here, right? And then what we are using to solve it is this base rule that we have written here. We are finding the probability of x given y and the probability of y. We are multiplying them together. And that's why you would see that instead of having y given x in our multiplication, we are having x given y. So that it doesn't confuse anybody when they are doing their revisions. Yeah? Is it clear? Is it clear? Okay. So now let's continue. What we have here now, what's left? So it's now for us to find the probability of y equals to 0 given x is equal to 1. So what will we have as that? 1 over 3, yeah, 1 over 3, nice. Then the probability of y is equal to 0 given x is equal to 0, x2 is equal to 0. So what do we have as that? Okay. Because we don't have that's it. So that's it. So now these two values, whatever we are going to calculate from here and here is actually not the probabilities per se. So you have to kind of normalize it. Yeah. So what you then do is that whatever you have, let's say we have P as our output from this and Q as our output for this. So the probability of having Y is equal to 1 is going to be P all over P plus Q. And probability of having Y is equal to 0 is going to be Q all over P plus Q. So this gives us the probability of having either Y equals 1 or Y equals to 0. So I don't know, it's because of time, but if anybody can quickly calculate what we have done here and then find the probabilities with what I have written here. Let's see what the probability of what our probability, which and I think if I'm to guess, let me see. I actually don't know, but let's see. Let's try it. It might not. It might be even. It might be close to 50. Two of them might be close to 50. Is anyone calculating, or should I just move on? Okay, seems like no one is calculating. Not calculating. Please tell me or anything. It's going to be quite inconvenient looking for. Should I move on, or if we understand it, then I can move
on. Sorry, can you explain that formula, because I can't see it well. The P over P plus Q, is that equal to G?
No, that's not J. That's not J. I just wanted to put this thing. That's not J. So the first probability, the probability of having Y, yeah, is going to be, sorry, is this expression here? Yeah, probability of having 0 is going to be this one here.
Okay.
So try it, let's see. Okay. Computer has an answer. So, okay, is it Q that is 9/10?
Q is 2/21. So I substituted the value for Q and P into the equation you put there, and that's what gave me 1/10 for P all over P plus Q, and 9/10 for Q all over P plus Q. For P specifically is 6/7. That's what I got, and Q specifically is 2/21. My calculations are correct.
Okay. Okay, that's nice. So you what you will notice now is that because of normalizes, we can say these are the probabilities, yeah? Because of course 0.9 plus 0.1, that's 1, yeah? And it's saying that it's 90% sure that the value that would have as Y is 0, right? It kind of makes sense too. Because if we look at, well, not too easy to visualize. Of course, you won't just consider the number of occurrence where you have x is equal to 1 and y is equal to 0. Of course, you won't consider all the cases where you have x equals to 1 and x2 is equal to 0, giving y is equal to, or where you have y is equal to 1, right? You also have to consider where you have your y as 0, giving x is equal to 1 and x2 is equal to 0, right? So if you check carefully, I think we have more, do we have more cases where x1 is equal to 1 and x2 is equal to 0? We actually have more cases where x1 is equal to 1. But what I have not looked at it carefully to know what judged the decision of the algorithm, but I think it works fine. But do we have questions so far from what we have done? Does it make sense? Like everything I've been saying, does it make any sense from this example we have given here? We are moving to code soon. Does it make sense? Please, I need to say yes. Yeah. Okay.
So the probability of sorry, I have a question.
Yeah.
The first probability that's of y is equal to 1 is equal to the formula we use, P over P plus Q, right? Then the other one, the Q over P plus Q is, sorry?
Sorry, I'm not hearing you clearly, I think.
Okay. Can you hear me now?
Yeah, I can.
Yeah, so the probability of y being 1, we said it was based on the formula of P, our value of P over P plus Q, right?
Mm-hmm.
Then the other one of y being 0 is Q over P plus Q.
Yeah.
Okay. All right, no problem.
Okay. So, so some potential issues here. So let's move faster so that we can move to the other part. So some potential issues. So what you would notice is that we didn't use the log, we didn't maximize or we didn't find the solution of the parameters using the log likelihood, right? We used the straight up formula using where we are having products like we had said here. I think we said it somewhere here. So this is what we did. This is exactly what we did. We didn't do this, and doing this here has some problems. There are some problems attached to doing it this way. And then what we are saying here is that. Hello. Okay. Please, can someone is not mute?
Sorry.
Okay. So what we are saying, what it's saying here is that these values that we are calculating, these values here, these values that we are calculating here, they can get very, very small. And because we are taking the product over all the data points, it can get very, very tiny and tend towards zero. Yeah? And if you're having products that are closer to zero, it invariably means it will go to move faster towards zero. It's not always going to be ones and zeros like we have here. It could be any value here. Yeah? And the solution to solving things like this, like where you're having products, is to use the log likelihood, right? Take the log likelihood. So instead of doing this, we want to do this because this it's a sum over all the data points instead of a product of the data points. So we are, even if it's small, we are not losing the information that our calculations is trying to show us, right? Then another thing is that here, what it's trying to tell us, what this second problem is trying to tell us, we don't need to look at it, I'll explain here, is that now, the reason why we're able to calculate the value of y is because we have every possible combination of x1 and x2, right? So we have x1 equals 0, x2 equals 0, we have x1 equals 1, x2 equals 0, x1 equals 0, x2 equals 1, x1 equals 1, x2 equals 1. We have every possible combination in this data set. But this might not be the case in real life, yeah? Because it's very possible you have more than one feature, and it might not be feasible for you to have every combination of all the features. And it invariably means that if you are going to be calculating, wherever your algorithms, if you give your algorithm a prediction for a combination it has not seen before, it is going to give it a zero classification, yeah, because it has not seen such combination before. And then the solution to doing that is to use something called the Laplace smoothing. You're basically adding 1 to the top and then plus 2 to the bottom, to the denominator, just like what we have. Remember, I told you guys earlier that another estimate is this. So it's just similar to what we have here. So this kind of accounts for scenarios where you don't have a combination and you are tasked to predict such combination. Yeah, it kind of smoothens it out, right? So you can actually still use it for other distributions. You can also actually use Bayes rule for other distributions. For the Gaussian distribution, where you are having your mean and your standard deviation over a normal distribution. Yeah. Sorry. Yeah. Not Gaussian this time around. Yeah? So if you're having a normal distribution, basically, you're having your mean and standard. It's still Gaussian though. Yeah, you're having your mean and standard deviation. All right, you can actually solve the problem of finding your mean, yeah, which we have also spoken about before, and your standard deviation using these formulas here, right? Okay, so now let's talk about the application of maximum likelihood in in some other machine learning algorithms. Yeah. So let's take, for instance, logistic regression. Earlier, we have discussed about logistic regression, right? And then we defined logistic regression with a loss that kind of decreases this way. Yeah, right? So, but ideally, what you have in practice today is not a logistic regression that uses this kind of loss. It uses the maximum likelihood estimate idea for its loss and optimization also. But what you would have instead of this is something called a sigmoid function or a logistic function, where you're having 0 here. I need to use my pen for this. Sorry. So where you're having okay. This is 0, and this is 1 up, and then flattens at 1. Yeah. So this is what you would have instead. And the idea that governs this whole logistic regression is still the your maximum likelihood estimation. Yeah. So this equation we have here is what we described in the previous class, and that is what gives us this graph. But instead of having this as your logistic to describe your logistic loss here, what we'll have instead is this. So this equation here is what gives us this logistic regression, this new curve that we're having here from 0 to 1. And so we are having 1 over 1 plus the exponent of, so the exponent as e raised to the power your minus y times h of x. Yeah, so this term here is usually you can actually call it your z, right? And we are going to be looking at an example of this in the next few minutes. Yeah, and okay. And if you're going to be finding the maximum likelihood estimate, you basically want to minimize. So normally what you would want to do before now, it's to minimize this, right? The logistic. So what we have here, what we do is we try to minimize this, yeah? But if you're going to be using your maximum likelihood estimation, what you want to actually do is to maximize this. It's to maximize the probability of predicting the correct y, as opposed to minimizing this value here, right? And you can actually still apply this to your least square algorithm here. Your least square algorithm. So remember the linear regression that we treated earlier, where we said the loss is your y minus your prediction, yeah, squared. So we also wanted to minimize this term here. But if you're going to be using the maximum likelihood estimate for a least square kind of problem or for a linear regression problem, you are going to be having the log of this probability. So you are going to be maximizing the probability of y given x for some set of parameters that you will define. Yeah. So this is just the end of the presentation. So let's go to something more practical. Yeah. Let's go to something more practical. I think we should be able to do it in the next 40 minutes. I just cloned. So this is the notebook in cloud on GitHub. So I cloned it so that I'll be able to run it. I don't know if okay, I think I'm not even sharing the screen. Let me see. Mm. 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 Where did I keep this thing? Sorry, give me 1 second. Trying to locate the notebook. Okay. I think I have it. Okay. Okay, can you all see my screen? If you can see the screen, just maybe raise your hands. So, okay, so we are good. So here you would see what logistic regression is, yeah, and how maximum likelihood estimation is applied to it. So this is something we did in cohort 3, yeah, cohort 3. Right? I think someone's unmuted. Okay, no. So as usual, we import the required libraries. Seriously, I don't have pandas on my system. Wow, this is embarrassing. Okay, so not to waste our time, I think I'll just use. Why shouldn't I have pandas on my system? I have pandas on my system. Sorry, please. Something is wrong. Sorry, give me 1 second. I think I'm not in the right environment. Let me launch my Jupyter notebook again. Give me 1 second. Think. Okay, I wasn't in the right environment. Source slash canon 11. Save it. Okay, it's good enough. Okay, can you all see my screen now? I think it should work fine now. Let's see. Okay, it's fine. Okay, I guess everyone can see my screen. Yeah. Okay. So as usual, import what the libraries will be needing: pandas, numpy, and the matplotlib. And so the data is this. The data we will be using is a TXT file which contains information about students who want to gain admission yeah, who want to gain admission, and their exam scores, right? The values on the first column contains the exam 1 score. The values on the second column contains exam 2 score. And the values on the third column contains the corresponding result, yeah, which is 1 for success and 0 for fail. So this is an example. This is more or less something similar to a real life example, yeah. And the goal of this example of this exercise is to use a logistic regression algorithm to use logistic regression and optimize and the optimization technique to generate a model that will predict the probability that the student will gain admission after 2 exam scores has been supplied. Yeah. So this is the problem statement, right? And our data is it's in this folder, data/x2data1.txt, and the columns. So we have to define the columns because of the way the data set is. So we have the data in the first column is, we named it x1. Second is x2, and third is y here. So if we run this, this is our data. So x1 is this exam score in exam 1, x2 is score in exam 2, and y is whether the person gained admission or not, right? So 0 means this person didn't gain admission. He failed the first exam and passed the second exam. This person, of course, I don't know, this person failed the both exam. Of course, he shouldn't gain admission. But surprisingly, we have 2 cases where the person did very well in the second exam and fairly poorly in the, okay, not fairly poorly, this is actually very bad. Still failed in the first exam. I didn't gain admission. So there are so many other things. So let's see the last, let's see what happens in the last. Okay, all these people are passing the exam. Okay, see here, this person passed very well in the first exam. I didn't pass so well in the second exam, and he still gained the admission. So it means that the level of failure you have in one of the exams, in as much as you pass the first exam, kind of determines whether you gain admission or not. Yeah. So let's change this back to head. Yeah, and move on. So the number of training examples we have is 100 training examples. We can find that by doing the shape. We can find that, dot shape will give us it's going to give us 100 by 3, right? And then if we are picking the first element of the what is returned, is going to give us the number of rows that we have, which is same as our value m, or the number of data points that we have. So we have 100 training examples, yeah? And we can pick out we can take out our values of x, yeah? So here we are trying to take the values of x and keep it in a separate variable, right? So here we are picking the value of x1 and x2 from this data frame here, converting it to an array, right? A NumPy array, and then we are saving it in xrow, right? And you see that the shape is this. So I'll be running it as we are going in. So of course, it's going to be 100 by 2, yeah? And then if we pick our y, it's going to be 100 by, it's actually 100 by 1, so it's 100 comma, yeah? So it's actually 100 by 1, right? So here in this, you all should actually try and go through this. Not you should try, you should all go through this node here to understand it on your own also. So I put some comments on some other things you can try out. So here, I loaded the data as to a pandas data frame so we can visualize it, but you can actually just load the data and convert them to a NumPy array straight away. So you can load them with NumPy. See here, I'm saying NumPy.load text. So here you are loading them to become a NumPy array straight away without putting them in pandas data frame first before converting it to a NumPy array. Maybe if you don't have time to visualize whatever you want to do, yeah, you can just convert to the NumPy array. But it's actually nicer if you're able to see what it looks like in structured format like this. So we can visualize what we have here, and you'd see that this is what the data looks like. So for this yellow point, circle points here, these are the people who are not admitted, and for this blue cross points, these are the people that were admitted, and it kind of has a nice distribution. Yeah, it's kind of nice, organized, unlike some data sets that you might see that some of these yellow points will find its way here. But truth is that most of the time you'll not find data in this format that's as neat as this, right? This is hypothetical data. So the next thing you would want to do is to stack ones to your X, right? So remember then when we were talking about linear regression and the rest, you remember we always stack ones for your bias, right? So it's the same thing we are doing here. So we want to stack ones to our X, to our input features here. And who can tell me what the shape of this X would be after stacking ones to it? So I'm stacking ones. So numpy dot c underscore is like stacking ones column wise, right? So you're stacking ones column wise. You're adding these ones of shape, this shape that's 100. You're adding it to your X row. So what will be the shape of X after stacking ones? Waiting for an answer. Or maybe no one can hear me.
Can you ask the question again so I can know
No
how
answer
to
it. I
answer
think
it?
just try, even if it's wrong.
Huh? Hello? Hello?
Hi.
Now, I was saying maybe if you could ask the question again so I can know how to arrange what I think is the answer. Thank you.
It seems we lost Kelechi.
Okay,
Perhaps.
actually, initially we had two columns for X, like there were in the first data we loaded, we had X1 and X2. And then later when we did the plotting, we had for admitted and not admitted. But I know when you stack ones with the value of X, it's supposed to be by side of two columns. As if X were to be just one column, when you stack it with ones, it becomes X1 in one column, then the ones in another column. That's like that's two columns for X. I don't know how to put it, like two inputs represent, instead of it to be one by one, or the rows by the column of X. That's number of rows by the column of X. It becomes number of the number of rows and the extra one column added to it. I really don't know how to put it. That's why I wanted him to re-ask the question so I can just put it with the same question he asked.
So I didn't know my network went off. I think I missed some things. What's can someone put me on track? I know I asked a question, what would be the shape of X? And I think Genevieve was trying to answer.
Yeah. I think she also said you should maybe rephrase the question. She mentioned that it would be row by column plus an additional ones. So if we had one column before with the additional one, that would be like n by 2. I'm not sure if that is what she means, but that was
Yes.
what I got.
Okay, let me kind of write it out. Okay, where's my pen? Okay. So I'm saying, okay. Okay, so remember we had extra is, or extra dot shape. Let me see, extra dot shape. Yeah, extra dot shape. Ignore what's on the screen though. Extra dot shape gives us 100 by 2. Now, and we know 100 by 2. Let's call 100 n, and this is m. Yeah. Or rather, that's not the convention. It is m by n. Yeah. And we know that n is our row and n is our column. Yeah. Yeah. And now we are saying that we stacked a column of ones. So if we had 2, so this is y. No, let's say this is not y. This is not constant content. We have x1. We have x2. Yeah. We stacked columns of ones, say x0, 1, 1, 1. So we stacked it. It was somewhere else. We just brought it and added it to this 100 by 2. What would be the shape? What would be the new shape of our x? So that's what I'm asking. I've already said the answer though. So, but maybe I didn't say it word for word. I didn't say the exact word. So, but I want you guys to tell me what it is. Okay, that's it. 100 by 3. Yeah. So we'll be having 100 by 3. Yeah. Okay, let's move on. Okay, so so we are almost set to pass in our data into our algorithm. So first things first, we have to define its. Remember, we said something about sigmoid function for logistic regression. So remember that 1 over 1 plus e raised to power, or the exponent of some values, yeah, the negative of a value. So now this is the formula that it is. That this is what we saw in the previous well, in the class or in the slides we're looking at before now, yeah. So for you to use logistic regression, first of all, if you're going to make prediction h of x is basically your g of this. So now, you know, before now we usually just do our h of is it h of x, or yeah, h of x, yeah. H of x usually is just usually your theta times your x, yeah. We usually have it as something like, where's this thing? We usually have it as something like h is equal to that's, say your h is equal to theta. Yeah. So, but now for logistic regression, this is not what we are saying. We're saying that your h is going to be your g of theta transpose times x. Yeah. I think this stuff is shaking again. Theta transpose times x, right? So that's what we would have. Where your g, yeah. So you are saying G a function of theta transpose times X, where your G is going to be equal to what? So take this term here, take it as Z. So where your G of Z, sorry, I think my notebook is open somewhere else. So where your G of Z is equal to 1 all over 1 plus E raised power minus Z. And this Z is equal to your theta transpose, is equal to your theta, sorry, is equal to your theta transpose times X, right? So this is our sigmoid function. This is more or less like what we use to estimate or to get hypothesis here. And we have to define it as a function. So the next step is to define it as a function. And I must say here that we won't go through the from scratch method of calculating, just like you saw in some of the other classes and the other notebooks. We are going to be using a library in this case, yeah. But the most important thing is for you to, there are some other libraries where you might not need to define all this, but for the sake of understanding, we are defining it and using a library where you can define it so that everyone can understand it better. Yeah. So next thing we do is to define our sigmoid function. So we are writing a function that takes in our Z, and we have all agreed, I guess, that our Z is equal to your theta transpose times X. Now, if we have this function, we have to find a way of calculating the loss. So remember in the previous, lecture notes that we just went through, I told you that you can use your maximum likelihood as your loss, yeah, to get to your loss. And that's exactly what we have here. So our cost function G, contrary to what you had seen in the previous notebook for logistic regression that we used before, what you would have and what is actually being used in practice now is something like this, where you are using your maximum likelihood estimation. So you are taking the log, finding the log loss of your H, which is your hypothesis, given Y, when you have your value of Y. So this is the negative log loss, I must say, yeah? And then you're having this also. So just like we have in the other case, if your Y, yeah, if your Y, that's your prediction, is equal to 1. Okay, now I need everyone to just answer this for me because I know I have said it countless times in the previous notebook. If your Y is equal to 1, yeah, what would be our cost function? What would be the equation for our cost function? What would be it? What would it be defined by? If our Y is equal to 1. Anybody? You don't need to type it on the, if you can just say it. Maybe raise your hand and I'll permit to speak. I said it like 20 times. The notebook.
Is it 1 minus X?
1 minus X? No. So when Y is equal to 1, look at the equation. So substitute Y is equal to 1 and see what happens. Okay, Obiora. Obiora, I can speak.
Okay, so I notice the second term in the bracket cancels out. It will be 1 minus 1. That is 0. 0 times whatever is 0. That's for the second term. So it means we have just minus log, then brackets, h theta of x as our.
Exactly. So this is exactly the same thing we were doing in the previous notebook. So let me go back to the previous notebook and show you all what I'm saying. How do I stop this? Sorry, please. I find it hard to. Okay. Okay. Come in, please. Can you see the slide now, or I see, what can you see now? Because it seems like I've lost track of. Let me try and share it again. Okay, you should be able to see what I have now. So what I'm trying to say now is that, remember, let me look for where we have it here. I think we have it somewhere. Sorry, please. Yeah, so this is it. So now remember when we said that if you're having your if it has a Bernoulli kind of distribution, remember we said that what we want to do is to maximize this. So if you look at this equation carefully, you'll find out that it's very, 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 very similar to what we have in the notebook here. Right? I think, yeah, we have in the notebook here. I think I'm still presenting the same thing. Wow. Why does this seem as if I'm showing the same thing? So which of the screens can you guys see? Because I think I've lost
The slides.
It's still the slides.
No, now it's notebook.
Oh, okay. So now the notebook. Okay. So so that's it. So now we've defined the loss function. The loss function. The next step is to so here we kind of used to compute the cost itself. We kind of used for us to compute the gradients and optimize to change the value to optimize the values of theta. We also implemented gradient descent, and of course you know that for you to use gradient descent you have to find the derivative of your j with respect to theta, and this is what we have here, right? So computing the cost is just what we have here, right? This computes the cost. This equation, this function here computes the cost. It takes in the initial values of the theta, the x values and the y values. Of course, we know the value of m, which is the number of data points. We can derive that from the x value or even the y value using the dot size. We know that the first element is the number of data points we have. Then we pass it through our sigmoid function, right? So you know our sigmoid function gives us the values, what we need here. That's our h. Yeah. So we pass it through our sigmoid function which we have defined here. And you know our sigmoid function is basically the z in our sigmoid function is basically your theta transpose times x. So that's what we computed here, right? Theta transpose times x, and that gives us our h. And then we pass this h into our formula for the cost function, which uses the maximum likelihood estimation, the negative log likelihood, yeah. And then we have our j, right? So we move forward and then define a function for the gradient. And the gradient of what we have written here is basically this, right? Is it this? Yeah. So this gradient kind of gives us the gradient kind of gives us it kind of informs us on how we can update our parameter. Yeah. And we define it here also, right? So the same thing, we pass in our theta, x, and y. We find our h using sigmoid, and then this is our gradient, right? And then we flatten it out. And then this is more or less like a test to just see whether what we have been saying from the beginning, whether it works. So let me run this, right? This is just a test function. So x is not defined. So it means that I didn't run this. Yeah. Okay. And then it gives us the cost and the gradient. So this is just random values. We are not optimizing anything. We are using random values of theta, and then we are computing the cost. And this is the cost. And then calculating the gradients. This is what we get after the gradient. This will be the values of theta, right? So this is just we defining the functions. Now, what we are going to do now is we are going to use a library called scipy to kind of pass in. We are going to pass in these functions that we have defined. So we are more or less defining our own functions, and then we are passing these functions to this scipy optimizing algorithm, and then it does the optimization for us. We don't need to write any what's the name? Any function to do that. So we pass into this minimize function. We pass in our function for calculating the cost. That's compute cost, which we have defined here. So this calculates our cost for us. That's how far away is it from the prediction. Yeah, the cost itself. Yeah. Then we pass in the initial value of theta that we want to use for the training. We pass in our x and our y. So you can actually define the method you want to use for the minimization, but none will just pick the default. Yeah, I don't know if the default is written here, but it's not actually written here. I don't think it's written. No, it's not written here. Then we pass in how we want to find our gradient. And then we've defined the gradient function here. And here we are saying, defining that this is the gradient that we want to use. And then the number of iterations we want to use for this particular task, we've set it to 400, right? So we pass this into this algorithm. It kind of calculates, does its own, it minimizes the function, calculates, and then finds the right parameters that, or the optimized parameters that can be used to make predictions. And if you print what you have already, we have said whatever happens here, we are saving whatever output that comes out of this into this res. Yeah. So if we print out res, we'll find out that we're having a lot of information, but what we need is the x here. So this is the weights. This is the parameters that we would use to make predictions, right? And it's the same thing we have here. Yeah. So if we want to test this, right? Testing this is basically, what it basically means is that we are picking these parameters, using these parameters to make predictions. Yeah. And you remember we said we are going to be using the sigmoid function, right? So now what we are doing here is that we are passing into this function theta x, and we are setting a threshold of 0.5. The reason why we're setting the threshold of 0.5 is, remember when I drew the remember when I drew the what is it? Okay. So remember when I drew this? Yeah. Oh, sorry. Sorry. Okay. Remember when I drew this? Yeah. So we said this is kind of flattening at, say, this is 1. This is the very wrong diagram. Please ignore. Let me draw it again. So let me start by drawing this first. Why am I drawing this way? Okay. Let me take it easy. Okay, let's say we have this. So remember we said this is 0, that's on the y-axis, and this is let's say 0. Let me put 0 here, and this is 1. Yeah, so you don't think this is 0 for y. We can say this center is 0.5. Yeah, your sigmoid function kind of goes this way. Oh, seriously? Hehe, I cannot draw again. Okay, so let me try it again. Kind of goes this way. Okay, so this is it. Something like this. This is what sigmoid function does. So what it does, you can call it a squashing. It kind of squashes whatever output you have from your theta transpose times your x. It kind of squashes it to be within the range of 0 to 1, right? So what you can now say is that what you can do is set a threshold and say that if the output of your sigmoid function is greater than if it's greater than, say, 0.5, that means the prediction is 1. Then if it is less than 0.5, that means the prediction is 0. Yeah, so that's why you use the sigmoid function. So now we are now setting a threshold to 0.5, and mind you, your choice of threshold depends on the kind of problem that you would want to you're trying to solve. Some people can set their threshold to be let's say it's breast cancer, for instance, where you have 1, meaning that the person has breast cancer, or 0, that the person doesn't have breast cancer. You would want to sometimes set your threshold to be 0.4, because if you kind of use 0.5, it's setting it at 0.4, it means that you don't want to take chances, basically. So if it's having something, if the output is something within the range of 0.45, 0.43, you don't want to take chances and say this person doesn't have breast cancer. Of course, this is an algorithm. You still want to take precautions to admit or test properly anybody that has a prediction close to being breast cancer. Yeah, so your choice of your threshold is totally dependent on you as the researcher and or you as a machine learning engineer, the kind of problem you're trying to solve. Okay, so now we define our test function. We pass in our theta, pass in our x, and pass in the threshold that we want to use. And then we use sigmoid. We pass in the theta and of course, this is our trained theta this time around. We pass in the theta, and then we want to test. And then the output of a sigmoid function, like 0 to 1. So whatever it gives you, you want to use a conditional expression here to check if it is. So now, if it is greater than the threshold, right? Greater than or equal to the threshold, it's going to return true. And if it is less than the threshold, it's going to return false, right? So what you're going to be having in your values of P is going to be true, lots of trues and false, yeah? That's what you're going to be having. And okay, so I'm thinking of how I'm going to show you guys. Okay, let me see. Let me try and see what happens. Okay, let's do this. So now you see what happens here. So what you're having as P. I'm printing P after this function. So what you're going to, but we don't need it to be to kind of find the accuracy of how well it predicted. Just to mention, we are testing against the same training set. Ideally, you shouldn't do that. You should do your test on some other data sets that you did not use for training, ideally, but because we have small amount of data set, that's why we're still using it for testing. So, but when we pass the values of X to see how it predicts whether the person gets admitted or not, you would have, after changing it to int values, that's changing the true false to int values, you're going to be having 1 for true and 0 for false, right? These are the predictions. So, but now, for us to get a sense of the accuracy, we have to check it against what the real values are. So we are now, here we are now calculating the accuracy. We are saying we want to sum over all the values where P is equal to our Y. So we are saying that if P is equal to Y, if our P is equal to Y in this particular data point, we want to have a true there. If our P is equal to Y in this second data point, we want to have a true there. If our P is not equal to Y in this third data point, we want to have a false there. So still you're going to be having a bunch of trues and false in this, for this computation here. And then you want to sum over everything that you have done. So if you're having ones for your P, and remember our P is 1 and 0s here. Yeah? So if you're having 1 for your P, ones for all the correct predictions and 0s for the incorrect predictions, if you are summing over everything, it invariably means you are summing for all the ones, because if you're summing with 0, it doesn't actually add to that sum. So you're summing for all the ones, and when you sum over for all the ones over all the total number of the data sets you have, you're going to have the accuracy for that particular task. Okay, seriously, time is fast spent. Wow. Okay, so now this gives us the accuracy. Yeah, and we have 89% as our accuracy, which is quite good, right? And we can plot to see how what the classifier looks like. Yeah, so we used a linear classifier, right? But if everyone will remember, when Teju was teaching in the last class, you can actually use something polynomial to actually define this better. Because if you remember, if you look at it carefully, it still depends on who the researcher and what he's doing. If you use a polynomial classifier, yeah, you'll be having something more or less like a curve, right? Instead of this straight line. Okay, so we can make predictions. So I wrote this function which everyone can just go through. For you, it just basically takes in some values and then gives your score. So over 100. Now let's make it more or less like a class thing. I don't want to give values. So over 100, where is this stuff? I hope I have not left the call.
No.
Okay, nice. So over 100, yeah. What is, give me, and maybe just pick someone's score. Just give me any score. Should I choose somebody to give us the score?
39.
39. Ah, the person failed. 39. Okay. 39. Exam 2. What did the person score in the second exam?
85.
Huh?
85.
85. Let's see if this person will get admission to UNILAC. So the probability the person will get admission to UNILAC is 0.5. And if you look at this plot here, this is where the person is. He's just on the line. So it's a 50-50 chance. He might get the admission, he might not get the admission. Right? So let's try another one. Someone else this time. Maybe a lady. There's somebody in this call. What was the name? That doesn't talk. Umu Kultum. So give us the number. Going, gone. Okay, another lady. Genevieve.
42.
Sorry, there's another lady. Please signify you. Like, I can't know all the ladies by their names. 45, yeah?
No, I said 42. 42.
42. Okay. Then, exam 2.
77.
Okay. CPT. You won't get the admission. I'm so sorry. So this is where the person, this is his position in the classifier, right? So now notice something. If say, let's take, for example, let's assume we didn't use a linear classifier. We are going to probably have, I'm guessing here, we are going to have something like, let me use my pen. Where's my pen? Where's my pen? We're going to have something like this. You might have something like this. Yeah. So now if we have something like this, would you really say it's a 27% chance of getting the admission? So you see that the choice of the model you decide to use, it's actually plays a very big role in the predictions you're going to get. So from the surface, yeah, it looks as if it's working fine, but it didn't work fine for this because, well, 42.77 is actually not too bad. If you ask me, I might still give the person the admission, even though I'm not but you guys can see what I'm trying to say here, right? So that takes your mind back to everything Tejus talked about in the previous class. Okay, so very quickly before we end the class, yeah, because I just have to go through the notebook. So I'll just glance through this because the deep learning class has to start now. So here we are looking at regularized logistic regression, right? So I'm sure everybody knows what regularization is because we have spoken about it. And I think I still showed you guys this notebook in the previous class, yeah? Yeah, I think in the previous class. So this time around, it's a different data, right? And this is what the data looks like, yeah? So it's, let me read what the problem statement is. So it says, here we're going to understand and implement the idea of regularization. We will implement regularized logistic regression to predict whether microchips from a fabrication plant passes quality assurance. This will be done from the result of two results. This will be done from the result of two features. It's actually features. Two features from two tests. Okay, yeah. So let me just for the benefit of that, what is regularization? Anybody? Or what does regularization do? If you don't know how to define regularization. Anybody? Nobody. Wow. Edry, where are you? Okay.
No, they're kidding, of course not. They're just shy.
I believe they are shy. Everybody.
I think it's like when you maybe multiply through, like maybe for instance, if you have a particular data set, you multiply through by a single factor, like maybe 2, 3, or 4 to make the data, like, I don't know, similar, to make it below a particular, I don't, just to shall make everything to be on the same page in a way. I don't know if that is.
So I think you are mixing up. I think you are mixing up normalization.
Oh, that's
No.
normalization. Well,
No, so that's actually not really normalization either. So that's why I say you are mixing two of them up. So it's as if you put two of them inside bucket, mortar, and you mixed it. So it's coming out as something. So okay, what is normalization? Let's start with normalization. Let's clear our mind with normalization. What's normalization? Anyone?
Can I try?
Yeah, yeah.
Okay. Normalization is what we do to make the parameters or the input, what we have to converge better. We found that when the values, let's say the values of x and y are on different dimensions. Okay, I'm trying to find the word. It's to help us help our algorithm to convert better. That's just the point, to convert faster. So that's why we use normalization.
Okay. So
And it involves using the mean. Sometimes you can subtract and the standard deviation from the figure, divide by the mean. Yeah, just so that's it.
Okay, so I'll start from the last thing you said. So it's not subtract from the standard deviation divided by the mean. No, it's the feature subtracted. You subtract the feature from the mean divided by the standard deviation.
Okay, thank you.
Yeah, and yeah, so it's more or less like you have large values as your x here, and you want to kind of reduce this large values such that there are smaller terms that would make your computation faster, right? And then also make your algorithm converge faster, yeah? So it reducing those values reduces the computation basically, right? Any other contribution?
Okay, and you mentioned regularization, and
Okay.
I think what I think Chisholm was trying to explain was that it keeps our model from overfitting to a particular
Exactly.
input. So that's what it does.
So that's it. It helps our our model not to overfit, right? So if that's why, if for those who were in the last class or the last two class, I can't remember which of them. You remember this plot where I said the one to the right because it's trying to learn every single detail in these data sets. That's why you're seeing it's trying to separate the plus the data points represented by plus with the ones represented by the dots. Yeah, and this is not because yes, it's going to meet new data from the world. If it learns exactly what is in this training data, it will not generalize well when it sees new data. It will only perform very well when it comes to this training data. And you know it won't always see the training data, yeah? Which is very bad. So, but when it generalizes well, it will give good probability of what should be. yeah, to give good probability of what should be. And the idea of regularization is more or less like tweaking the values of your theta or reducing the values of your theta such that it doesn't get too complex and learn everything here. It kind of smoothens it out, and that's why you have something like this. But you have to have it. There should be a balance between you have to choose the right regularization parameter to have good results. Because if you are using a very high value for your regularization parameter, and you'll be having something like this, it won't learn well because we've not even started looking at the problem. Or maybe I should leave everyone to look at the problem. Maybe I'll just explain it briefly. Okay, because we are already out of time. So let me start from it. So this hello, I'm really sorry. I don't know. Network. Can you hear me?
Yeah.
Hello. Okay. So uh, so this is where we're. So training examples we have as usual. We take out the features, which is x1 and x2, and the ground truth, which is y, and save them in variables, and then we can plot, right? And then this is what our plot looks like. Of course, everyone will know here that you cannot. I don't know how you want to use a linear classifier for this kind of data set. You need something that kind of gives you it's the polynomial you basically need, something that kind of gives you a circle, something that is more complex than what the linear classifiers that you have, right? And of course, what we are going to be using here is the polynomial kind of model that we'll be using here. So remember, then we said what you have as polynomial model is something similar to this, but we are not going to define this with our hands here. So there's a function in sklen that kind of gives us a polynomial kind of model. It returns a polynomial kind of model. It kind of increases the number of features, right? And it's increasing the number of features to kind of give us that polynomial thing that we are trying to achieve. So now we want to get a polynomial feature to the power of 6. So we want to get a polynomial feature whereby our n in this equation we're having here is to the power of 6, right? Okay, I think I ran this. Okay. So this is so it's a mapping though. So this is our mapping. We say that it is to the power of 6 and it includes a bias. So we don't need to pass in a bias, right? And what we now do there now is to pass in our x, because of course it's our x that we want to increase. You have nothing to do with y here, right? We're just going to increase this to a polynomial function, and then we still have our y. We will pass it into this mapping that we have defined here, this mapping function we have defined here. It returns a shape, that polynomial thing that we are looking for, that polynomial distribution kind of that we are looking for. And then this is what it is here, right? So we're having x underscore rho mapped.shape is 28. So we're having 28 new features, or the features now is 28. So we're having the 118 by 28. And then we use the normal logistic regression formula for calculating our J, which is the maximum likelihood estimation, and then we add our regularization here. So this is the regularization parameter, lambda over 2n, sum over the theta, right? And lambda is our regularization parameter, if you all remember. And then we define, like we have done above, we define the cost function. We define the cost function equation, similar to what we have, but the difference now is that we are adding our regularization here. We define our gradient. So for our gradient, we're also adding regularization. So this is what it is here, right? So this is the function here. And then, like we did before, we test. Okay. Okay, sorry. I didn't run this either. So for the test, and then like we did before, we just pass everything to our we pass everything to our minimize function that we had, like we used in the earlier example, and then we train. So this is what it looks like. This is, so now we are going to have more parameters. We are going to have way more parameters. Where is it? Where is it? Where is it? Where is it? So now this is our parameters. We are going to actually have about 28 parameters because the number of features have increased. So the more your parameters, the more complex your algorithm is, right? So you are using a polynomial function to increase the complexity and understand the distribution of your data better. But in as much as you are making it very complex, you need to kind of tame, let me use the word tame, you need to kind of tame its ability to be very complex. And that's why you're using a regularization. You're using regularization to, let me use the word tame, right? And then we can test. So this is our X, these are our parameters. And then we can test, right? So when we test, so that this is the test. So when our regularization was 0, we had an accuracy of 91%. So we didn't regularize at all. It looks as if, oh, it's perfect. But in the real sense, it's not perfect, yeah, because it didn't generalize well. If it says new data is going to perform badly. But when you regularize, it has 82%. Trust me, this 82% model is going to perform way better than this 91% model. But now if you over regularize your parameter, it's going to perform very badly, and that's why you're having 60% here. So this is just an indication for every one of us by the time we start doing our projects. It's just for us to understand that you have to take into account all these concepts when you're training. In as much as you're going to be using libraries, right, you should also understand what your learning rate does, how it works, and how to choose the right parameter values, what your regularization parameter does, and how it works, and how to use the right values, and what algorithms to use for particular tasks, for different tasks here. So I've already explained this. We already know what it is, right? And then we can predict. So prediction here might not be too intuitive, though, but because I don't know anybody that works in a fabrication company too. So, but it's just like the other, this predicts the probability of having a pass or a fail, right? So that's the end. This is just a small practice I put in the previous stats for those who need to understand slicing and the rest. Yeah, so it's just for everyone to look at when you have the time. So I think this is the end of the class. I hope everyone understood this notebook. Does the notebook throw more light to how you can apply it and how you can use this thing? There are libraries that might be simpler than this, though, where you don't need to define the function, but it's whatever suits you that you go for. I'm saying this because of the projects that everyone is going to work on, right? So, but Does everyone understand everything I have said so far? Right? Hello?
Yeah, to a good extent.
Okay, Fortune has a question. Fortune, you can speak.
No, not a question. I was saying I understand.
Oh, okay. I'm happy today. I'm happy today. I'm happy today. Okay, so everyone will need this. Okay, almost says not completely. Okay, maybe we can talk maybe after, on Slack, yeah. Maybe we'll discuss on Slack and then we'll go through any parts that you don't understand. But what you can do for me is try and go through. If you didn't get what we did in the notebook, if you didn't get all the mathematics, at least you should get some concept from it. So what you can just do is to go through this notebook, and anything you don't understand from this notebook, we'll look at it together. That the same goes for everyone on the call, yeah. And you can also discuss with everyone in your groups, and you can say I will have a concrete understanding of this, yeah. So because I know some people won't read their emails, I have put a link. I hope I put that link. I put a link to a post. I think it's on Towards Data Science on algorithms that you can use for your projects. So in as much as we have gone through just some few algorithms, logistic regression, knife Bayes, linear regression, it doesn't mean that you are limited to those algorithms. Yeah, they all have the same concepts, but different probably different methods or different formulas and the rest here. So, but you are open to using any algorithm you want to use. And on that post here, you would see different algorithms you can use, and you can read more about these algorithms. And I think there are videos attached to them on how you can implement these algorithms using some special libraries. Yeah. And it's just for everyone not to get confused on how to start. Yeah, so you'll probably want to go through that document first and know which projects you want to work on. So I think that's that. Does anybody have any other question? And then I would also send the link to this this notebook. I'll send it after this call. Yeah. Is there any other question?